and everyone, especially to Dr. Indangan. Sir, good afternoon. My task is to report Chapter 22, Multiplicity of Roots. I am Charity Pate Pili Batog, Best Ed Math 3, one of your discussant in this afternoon. Without much further ado, let's find out what is multiplicity of roots. So, multiplicity of roots, if f of x is a polynomial over big letter k and c is a root of f of x in some failed big letter f containing big letter k, then the multiplicity of c is the largest positive integer m such that quantity of x minus c raised to the power of m divided f of x over big letter f. In the definition 22.1.1, let big letter k be a failed and p of x be an irreducible polynomial in k of x of degree n. Then p of x is called separable if it has n distinct roots in a splitting failed big letter s of p of x over big letter k. Otherwise, p of x is called inseparable over big letter k. An arbitrary polynomial in k of x is called separable if each of its reducible factors in k of x is separable. Otherwise, it is called inseparable. In the definition 22.1.2, let big letter f over big letter k be a failed extension and c be an element of big letter f which is algebraic over big letter k. Then c is called separable or separable algebraic over big letter k if its minimal polynomial over k is separable. Otherwise, c is called inseparable over big letter k. If big letter f over big letter k is an algebraic extension, then f over k is called separable or separable algebraic if every element of f is separable over k. Otherwise, f over k is called inseparable. Let f over k be a failed extension and let an L be an intermediate field of f over k. Let c belongs to big letter f and suppose c is separable over k. Then c must be separable over big letter L. This follows since if f of x and p of x are the minimal polynomials of c over big letter k and big letter L, respectively, then p of x over f of x. Hence, c cannot be a multiple root of p of x since it is not one of f of x. In the theorem 22.1.4, let k be a failed and f of x belongs to k of x. F of x is not equal to 0. Let a be a root of f of x in some extension field big letter f of big letter k. Then a is a multiple root of f of x if and only if a prime of a is equal to 0. Proof. Suppose a is a multiple root of f of x, then quantity x minus a raised to the power of 2 divides f of x. Hence, f of x is equal to quantity of x minus a raised to the power of 2 times g of x, for some g of x belongs to f bracket x. Now, f prime of x is equal to quantity of x minus a and set of x minus a g prime of x plus 2g of x. Therefore, f prime of a is equal to 0. Conversely, suppose f prime of a is equal to 0. Then dig f of x is greater than or equal to 2. By the division algorithm, f of x is equal to quantity x minus a raised to the power of 2 times q of x plus h of x. For some q of x, h of x belongs to big letter f bracket x, where either h of x is equal to 0 or dig h of x is less than or equal to 1. Suppose h of x is not equal to 0. Hence, f of a is equal to 0, h of a is equal to 0. Thus, the h of x is equal to 1 and a is a root of f of x. Hence, h of x is equal to b times x minus a for some 0 is not equal to b belongs to big letter key. This implies that f of x is equal to quantity of x minus a raised to the power of 2 times q of x plus b times x minus a. And so, f prime of x is equal to quantity of x minus a times set of x, quantity of x minus a times q prime of x plus 2q of x plus b. Therefore, 0 is equal to f prime of a is equal to b, a contradiction. Hence, h of x is equal to 0, and so f of x is equal to quantity of x minus a raised to the power of 2 times q of x. Consequently, a is a multiple root of f of x. Theorem 22.1.5. For any failed big letter key, an irreducible polynomial p of x in big letter key of x is separable if and only if p of x and its formal derivative p prime of x are relatively prime. So proof. Let d of x denoted the GCD of p of x and p prime of x. Suppose p of x is separable. Let C be a root of p of x in some field containing big letter key. Then p of x is equal to quantity of x minus 2 times f of x for some f of x belongs to big letter key of C times bracket x. Since p of x is irreducible, f of x is not equal to 0. Now, p prime of x is equal to f of x plus quantity of x minus c times f prime of x, and so p prime of c is equal to f of c plus 0 is not equal to 0. Hence, c is not a root of d of x. But every root of d of x must be a root of p of x, since d of x over p of x. Thus, since we have just seen that d of x and p of x have a common roots, d of x has no roots. Therefore, d of x is equal to 1. Conversely, suppose that d of x is equal to 1, let c be any root of p of x, let m denote the multiplicity of c, then p of x is equal to quantity of x minus c raised to the power of n times f of x over big letter key of c, and c is not a root of f of x. Now, p prime of x is equal to m quantity x minus c raised to the power of m minus 1 times f of x plus quantity of x minus c raised to the power of m times f prime of f of x is equal to quantity of x minus 1, quantity x minus c raised to the power of m minus 1 bracket m times f of x plus quantity of x minus c times f prime of f of x. Thus, quantity x minus c raised to the power of m minus 1 is a common divisor of f prime of x and p of x. Is a common divisor of p prime of x and p of x. Hence, quantity x minus c raised to the power of m minus 1 over d of x. Since d of x is equal to 1 and then m is equal to 1, consequently, p of x has no repeated roots. In the theorem 22.1.6, for any failed big letter key, an irreducible polynomial p of x in k bracket x is separable if and only if p prime of x is not equal to 0. So proof. Let d of x denoted GCD of p of x and p prime of x. Suppose p of x is separable if p prime of x is equal to 0, then d of x is equal to p of x is not equal to 1, a contradiction of theorem 22.1.5. Conversely, suppose p prime of x is not equal to 0. Since p of x is irreducible, the only common divisor of p of x and p prime of x are 1 and p of x. Since 1 is less than or equal to degree p prime of x, less than degree p of x, 1 is the only common divisor of p prime of x and p of x. Hence, d of x is equal to 1. Thus, p of x is separable by theorem 22.1.5. Example 22.1.8. Consider the irreducible polynomial p of x is equal to x raised to the power of p minus t raised to the power of p over k of t raised to the power of p of example 22.1.3. Then p prime of x is equal to p of x raised to the power of p minus 1 is equal to 0. Thus, x raised to the power of p minus t raised to the power of p is inseparable over k t of raised to the power of p. In the theorem 22.1.9, let k be a field of characteristic p is greater than 0. Then an irreducible polynomial p of x is equal to k sub 0 plus k sub 1 x plus k sub 2 x raised to the power of 2 plus plus k raised sub n x raised to the power of n over k is inseparable if and only if p of x is equal to q quantity of x raised to the power of p for some q quantity of x raised to the power of p belongs to k bracket x raised to the power of p. Prove clearly that p prime of x is equal to 0 if and only if I k sub I is equal to 0 for all I is equal to 1 to ... and thus p prime of x is equal to 0 if and only if p over I for those I such that k sub I is not equal to 0. Hence, p prime of x is equal to 0 if and only if p of x is equal to q times x raised to the power of p for some q of x raised to the power of k belongs to k x raised to the power of p. The conclusion now follows from theorem 22.1.6. And thank you for listening. That's all. Thank you and God bless.